So I thought that this handout could actually help us kind of get through some of this a little faster, as I put down the most important things that I wanted to cover today. Do you all have anything, just before I get into it, anything on your minds that we need to talk about? Cool, great, I love y'all, thanks. Let's get going. So properties of cosets. Just like in your brain, what's a coset? Don't say it out loud, what's a coset? Anybody feel like sharing what's in your brain? It's not appropriate what's in your brain. Christian, what is a coset?
So if you have a set H and a group G, the coset H in G is like you take an element from G and multiply it by, or like operate it on every element in H.
Yes.
Missing something.
There's one thing. What would I tweak in what Christian
Would it
said?
be like an element of G, like you selected?
Element G, but what is H? It's not a set. It's a subgroup. So the H has to be a subgroup. We first defined that operation of A times H as a set, but a coset is
a subgroup.
Right. So we've got a group G and a subgroup of G. And then, as you said, we take some element from G and we form this coset, which basically means take everything inside here, inside H, and left multiply by A. So we have these left cosets and we also have right cosets. And if our group is non-abelian, these might not be the same thing. It could be different beats. We saw that actually, right, with some example from S3, I think.
Does H have to be a proper subgroup of G?
Not necessarily, no. It could be all of G. What if it was all? Oh, I like that. What a cool question. So what if H equals G? Then what are my cosets? Just G. Yeah, it's actually then if I take A times G, it's just kind of just one of the rows in the Cayley table, right? So it would be just whatever it permutes the other things to, right? So, whatever. Yeah. That's a good question. And it could even be a trivial thing. Could be the trivial subgroup E, which would be pretty boring as well. But that's about as granular as it could get. And we're going to see what these things do a little bit more today. I hinted at a lot of things. But let's look at these properties of cosets on the front. There's two sides to the handout. First off, what's the proof of one? Can somebody walk us through the proof of one? Is that for any element A in the group G, A is an element of AH. Why is that?
Well, if it's AH, it has to be in it because it's in AH.
Well, what's in H that would?
An identity.
The identity, yes, exactly. Yes, so we know that H contains, E and a bunch of other stuff. So A is an element of AH because A times E is an element of AH when H is a subgroup. And is this what you were trying to say, Sophie?
I think so, yeah. Yeah.
Cool, okay, cool. So good, so that's kind of the proof of that one. Let's take a look at number 2, which was something I started stating at one point, and then I think we came up with this definition, but let's take a look at it. Number 2 says that the left coset, or this could be a right coset, of H generated by A. So this is the representative, times H is equal to H if and only if A is actually an element of H. So now one of these directions, this direction's pretty chill. In fact, it's almost kind of like what we were just arguing. So if A is an element of H, let's do this direction here. If A is an element of H, E is also an element of H. Let me slow down. So I'm taking this, and I want to show this. How do I I show this? What has to be shown here to show two sets are equal?
Both, or like, so you have to show AH is a subset of H and H is a subset of AH.
Yeah, exactly. So we're gonna assume this, and then we would need to show that this holds true and this holds true. So why is this one true?
Didn't we, like, no, we didn't show that.
What does this mean?
Well, so A is part of H, so you know that if you're operating A on that entire set by group closure, right, you're just gonna get H back.
Yes, yes,
You
exactly.
can't get anything that's not already in H.
Exactly, so this one is closure of subgroups. Because once I know A is already in there, then A's inside here, so this would just create A squared, which is already in H because it's closed. So this is by closure of subgroups. What about this one? So we know A is in H. Why is H a subset of AH?
Well,
Yes, so-
because H is in H, like H is H, so if you add something to it, H is still gonna be fully there.
Yeah, so let's, yes, I think so. So I'm gonna take an H, I'm gonna take an H out of here. Why is that H over here? So I've got an H here, I need to show that this H is an element of AH. How do I do that?
Take A from H and operate it on little h.
So I'm gonna take, all right, so we take this guy here, and then you're saying left multiply by A.
I think so. And then won't that be in A big H?
It is, but it's not my original H. You're right. You're absolutely right. But I need to get just good old H in there. Why is that in there?
Multiplied by an A inverse.
That sounds good. So check this out. So if H is in here, we need to show that H is also in here. So what does this mean? This means that H is equal to A times some H prime. It may not be the same element. So to show this, I need to show that this thing here is actually of this form. So I'm going to let H prime be A inverse H. So let that, now this is definitely, let's see, wait, this is an element of H, why?
Because
A is an element of H.
Because I heard a couple reasons.
A is an element of H and H is a subgroup, so A inverse has to be an element of H.
Exactly, and we assumed H was in there. Sophie, is that, yeah, does that sound good? So does everybody see that? We know that we assumed A was in there, so A inverse is an H. We assumed H is an H, so that's in there. And then by closure, these are both elements of H. So now if I take A times this H prime, that is definitely in AH, because this H prime thing is in H. So then, let's see, and this is equal to A.
Equal to H.
Equal to H, thank you, yes, thank you. That's equal to H. So it's kind of subtle. Do I need to make that argument clearer, because it's a little sloppy? Would anyone like that to be more?
And that's equal to H because you just left multiply by A, and then you get.
Yes,
Okay.
yes, exactly. Because I'm letting H prime be A inverse times my H here. Okay, I'm seeing some yeses, but I'm happy to make it clearer for anyone who would like that. Just like put a thumb up. A thumb up if you want to see it better. 2 thumbs up. Man, I got 2 thumbs up. All right. Okay, so we've got that guy pretty much rocked out. Let's look at 3.
Do we still need to go the other direction? direction for?
Oh, did we not go the other direction? Yeah, let's see, so which direction have we gone? Oh, we just did this, right? So, yep, thanks, Abraham. So now, let's us show that AH equals H implies A is an element of H. Can you try that? These things are simple, but they're a little painful too, and it's good to like just suffer with it a bit. Just to help a little bit, writing out what that hypothesis means, that AH is equal to H. And once you start getting used to writing it out like that, you kind of get how all these proofs go in many ways. This is, what I've written here is actually just this inclusion. There's a similar statement that goes the other way as well. Anybody got a proof?
We know H inverse is in H because it's a subgroup.
Okay, so yeah, so where are you starting at, Abraham?
So I'm just gonna start with assume AH equals H.
Okay. Cool.
And then we use that part on the left where, oh wait, is oh, I'll be lost, never mind.
It's okay, it's okay, it's easy to get lost. It's easy to get lost here.
Are you not able to just say like?
Yeah, maybe something easy. What you got?
If, so you know H is a group, like H has group structure.
That's right.
So you know it's got closure.
Yep.
Which means that like with equality, like AH would also have to have group structure,
Yes.
right?
Well, not necessarily. So you don't get that group structure with the cosets, alas, right? The only time you do is when A is actually already in.
But if you know that AH is equal to H.
Yes.
Do you not have group structure for AH? Like, cause you know that H is a group.
Yes, but AH doesn't have that group structure. But there is something in H that would make that, there is something about the group structure of H that does make this quick.
If AH equals H, does that imply A inverse is in H?
It does.
So that's one thing you need for it to be, oh wait.
What's in H that's like the easiest thing in H?
The identity.
The identity. So look, this is saying that everything in H, when I take A times anything in H, I land back in there, right? Does that make sense? That if I take A times H, so for all H and H, A times H is back in H. Does that make sense?
Are you gonna let A be the identity?
I'm gonna let H be the identity.
Oh.
So, in particular, if E is an element of H, so AE is an element of AH, which is equal to H, so that gives me A is an element of H. Or AE is an element of H. Maybe if I went, so AE is an element of H, so that. It's weird, tricky stuff.
Like, so for the A
Yes,
and
sir.
H
Yes.
is an element of H.
Yes.
Is that, I guess I don't see how that's not closure of like groups. Like, I
Because,
understand that you're getting that from like the idea that, not that A is in H, but just that if H is in, like little h is in big H, right?
yes,
And H is equal to AH, that's kind of where that's coming from,
yes.
like through that equality, but I guess I don't really see how we don't already have that group structure through the equality.
But this A doesn't necessarily, here we don't know yet that that A is in H.
Okay.
Like, right, because that's where I'm going to. And I think
Okay.
in your mind, you're putting it in H,
Yeah. Alright,
but we don't have that yet.
okay.
But I do know that E is in here, so A times E is in here, and so A has to be in there. Sophie?
Can we build on the stuff that we've already proven? Cause didn't we just show that exact thing in one?
What we showed, oh, did we already,
I mean, we already
The A
showed,
is in AH.
so can we just say, like, according to our proof for one, that works?
yeah, I guess we actually could. Yeah, you're right, yeah, we could.
Okay.
We could actually remember something that happened 5 minutes ago. Yeah, that would help. So Sophie's saying that we know this is the case. So if AH is equal to this, A is an element of this, therefore A is an element of that. I think that's a better proof. That looks nice. Yeah. That's good. That's good. Well, if people furrow their brows at what I've done up there. What do you think about 3? You believe me?
I'm not gonna lie, not really, but the thing that, if A is an AH,
Yeah.
then A is an E, or H.
Yeah, you buy that
I
one.
buy that a little
Okay,
bit more.
all right.
Yeah. I guess like, yeah, so AH equals H, like where I exactly do like, if you have like a set is equal to a group, right?
Yes.
Just in general.
Okay.
Does that not make that set a group itself?
Wait, so if a set, say what you say that
Like
sentence
if you
again?
have like a set
If I have a set,
is equal to some group,
doesn't that make it a group though?
that's where I'm at, like.
I mean, if I have a set that's equal to a group, yes, I mean, in this case, that does have group structure, but only because A is in the H itself would it
Okay.
have that group structure. Because cosets in general don't have
Yeah.
the
Like
E.
I
right?
see what you're,
Yeah,
what you're
yeah.
talking about, yeah, I guess it is probably kind of like relying on like A being an H, what I'm trying to say, but.
I think it is, I think
Yeah.
so.
Okay,
Oh,
that,
yeah.
I follow.
No, this
Yeah.
stuff's like so weird and like right in front of you that it can be a little baffling. Let's see, I'll put up here. And we can probably use some results that we've already proven. AKA Sophie's theorem.
Yes.
direction's pretty chill if we use property one. If we assume AH equals BH, then by property one, we already know A is an element of this guy. And if these two are equal, A must also be in the other one. So that direction falls pretty naturally from property one. What about the other direction? There's a little hint up there that if you're not quite sure where to proceed down that other path. What's up? Yeah.
If we know that A equals BH, can we also rearrange and say that, B equals AH?
We, close, we can say B equals AH inverse. Yes, but we can. And because H is a subgroup, H inverse is also in it. So absolutely we can. Yeah, feel cool? Yeah, that's it. Yeah. He's living in a cold.
Yeah. 100%.
Yeah,
Really
I'm-
weird algebra.
Yeah, I'm not sure, I was chasing this idea down, I don't know, because we do wanna show, that this means A is an AH, so.
Well, I guess my thought was like if you substitute A and B, so substitute A with BH, and then substitute B with AH. Your original.
Oh, do you mind?
Yeah.
Yeah, it's just like all these, like saying it, there's too much shit going on, but,
Lowercase
yeah,
letters.
yeah.
But I'm thinking like if you do, instead of, like you take A, and we know that A is BH, then you can do, and then you know that B is, and then you can do some weird algebra and simplify it, but I don't know if that actually works.
Yeah, I think that can give us some intuition, but we have to work on on like an element
Yeah.
level. But
Yeah.
yeah, I think, yes, that's probably,
That was like the direction that I was gonna take that.
Yeah, yeah.
If you have to do it from like an actual, yeah.
so wait, what are we assuming? So we know that A is in BH, right? So we've got A is in BH. And we wanna show, let's see, I gotta write up, I always have to write up what I'm trying to show. Keep things on track.
Oh, do you have to show like AH is a subgroup of BH, BH is a subgroup of AH?
Yes.
But now you know A is included in BH and B is included in AH.
Yes.
So are you?
Yes.
Out there, pretty much.
Yeah, it does feel.
Would you be able to write multiply, I guess, by like another H?
On this?
Like,
Or
or I guess for like the,
are you thinking this?
for A, so for like the A equals BH, right?
Okay.
If you write multiply that by H, right, by like some H in H, I guess, wouldn't you get that AH is like, I don't know what I'm doing.
Okay, let's take a look here. It's funny, I was proving this stuff like, Sophie, I'm gonna erase this, if that's okay, sorry. Okay. So, let's leave that up here. So we've got that. We need to show that everything that's in AH has some companion in BH. So let's say we want to show this first. And sometimes just going and writing down these step-by-step things can help your brain a little bit here. So I'm going to take some Y in AH and show it's over here using these relationships that we've got right there. So I'm taking a Y out of this side. That means that Y is equal to AH for some H in H. This is the only way I can ever think about this stuff. And now at this point, I need to show that this Y is also B times some element of H. But I can do that by, yeah, do you see our trick maybe right over there? But A is equal to, maybe we should use H prime here because we already got an H up there. So let's do that, so they're different. But A is equal to BH by hypothesis, by this and then that, just that first line right up there. So Y equals BH, H prime equals, do you see where I'm going with this?
Mm-hmm.
This is reassociate. Why is this in H?
H prime is
Closure.
an H.
That's the element.
Yeah, it's closure, yeah, right, because they're both in H already.
Yeah.
So this is an element of BH. So I feel like just slowing down and trying not to bite off too much at once is like a lot less painful completely. We might even need this on the second side. Let's do the other direction. Is this feeling okay here? This, okay, so let's try the other. Now let's show that BH is a subset of AH, and I kind of got a feeling this relationship is going to come into play here. Why don't you try that? And try that, pick a Y out of BH or a Z out of BH. And then what does that mean about it? We do need that guy right there. It's the same game, but we need the flip side. So we definitely needed that guy to move between A and B. We need both these relationships. And they came from this assumption right here.
I have a question.
Yeah.
What's the application of this? Like, I'm just thinking about like.
We will apply it shortly.
Okay,
It's kind of a tool for proving some bigger results.
okay.
And then doing a bunch of other weird shit that we haven't got to yet.
Yeah, I think that's my challenge is like at this point I don't see like what it is a part of.
It's, in some ways, it's like a prism that you're running the group through and breaking it into some almost kind of fundamental frequencies in some ways to get a basic understanding of the structure that lies underneath.
Okay,
I just made that shit up, but that sounds pretty good.
sure, I'll take
Shit,
it.
I know, I thought you'd like it. I thought you'd like
Yeah,
prism.
Yeah, that works.
We got B equals A H inverse just by multiplying by H inverse, right?
Yes, took this guy and multiplied by, yes, sir, yes. And then I flipped the order, here's the sides of it too, yeah. Other questions? Because the next one is kind of a big one. And this one tells us something that we've been seeing and I've probably mentioned, but we haven't ever proved it. So let's talk about number 4, that if I have a subgroup H and I form cosets, the cosets, 2 different cosets are either exactly the same thing or they don't touch at all. They are completely disjoint. So number 4 says that you have 2 cosets. You got AH and BH. Those suckers are either the same coset or they are completely different beasts. So this is a cool proof. And it's gonna remind you of a proof that we did just pretty recently here. So let's do the proof together and I'll take away the pain we can talk through hand in hand. I'm going to assume, so if it's empty, then I've proven that. If the intersection is empty. So if AH intersect BH is empty, then we're done. Cool, let's assume it's not. And then show the other thing must happen. If AH intersect BH isn't empty, then there's something in common between the 2 of them. They have some element. Then there exists some Z in AH intersect BH. Why does that make them the same? I'm gonna give you a minute. Why does that mean that AH and BH have to be the same? So why then is AH equal to BH? You have a link now between the 2, that Z forms a bridge. How do you use that bridge? So if you take something out of here, how can you use that Z to get over to here and vice versa? And once you see one direction, you'll get the other. But this is our link right here. And just so it might not be the same, right? So it could be 2 different elements. It probably is 2 different elements of H if A and B are different. So I can write Z like this, and I can also write it like this, where H and H prime are elements of H. So now you've got a bridge.
Can't we say that from the previous proof, we know that Z is in, like the A of H and B of H at that point?
So wait, so from number 3 there. I mean, definitely the clue to getting that equality is to use number 3 for sure. So you don't have to do the double inclusion because number 3 gives us what we need to show. I think that's what you're saying, right?
Something along those lines.
Something along those lines. Yeah, but use the number 3. You just need to show the second half of that biconditional. Why does this mean A is in BH? Okay, you see it? You see? Let's start going down. Somebody walk me through this. How do I do it? So how do we see that A is in BH? So A equals what?
A equals B, H prime, H inverse.
Ooh, you're moving fast. Yeah, so you took that guy and solved that for H, right?
Well, I started with AH equals BH prime.
Oh, I like that. Oh, that's better. Okay, so AH equals BH, right? Oh, that's a cool one. Yeah. And then
A equals BH prime, H inverse.
Yeah. Nice. And that's just an element of H. Yeah, beautiful. And by 3, AH equals BH. Cool. Good. Let's see, what about that next one? Where the hell's my note sheet? Next one, fairly chill.
Do we have to show that B, like it works for BH as well? We showed it works for AH.
So if we use that result 3, we don't really need to, Sophie.
Oh, cause it goes both ways.
Yeah, because it could, yeah, exactly.
So we can show it one way.
I mean, you could show B is in AH, either one of those will get you, they're both equal.
Okay.
I'm gonna kind of skip 5 because we don't particularly need it, but do you see how that might be true? Well, let me just kind of quickly move through it so we can see it together without a super formal proof of it. So here they're asking us to show AH equals BH if and only if A inverse B is an element of H. And we're gonna go back to, well, we could use 3 or 4 here. If we can show that there's some common element in AH and BH, then they have to be the same. Or we could go to number 3 and show that if does this imply that A is an element of BH? Or B, how about this? Is B an element of AH? Let's see if we can see that. So this thing here, let's assume this. Let's assume A inverse B is an element of H. So in other words, A inverse B equals H for some H. And then I think the thing I kind of wanted to show you here today when we went through these was just grabbing an element and working from it, right? Quit thinking about the whole subgroup and just grab somebody out of it and then do some algebra. So how are we gonna get B as in AH from that? It's not too far a move.
Just let multiply.
Left multiplied by A, right? So B is equal to AH, which is definitely an element of AH. And because of that, AH equals BH. And if AH equals BH, let's go the other way real quick. if AH equals BH, then how do we get this? Well, this means there exists H and H prime in H such that AH equals BH prime. How do I get A inverse B in H from that? So how are you gonna get A inverse B? I mean, think about what we got here. How do I get an A inverse B into this expression right here?
Just left multiply by A.
Left multiply by A inverse. So if I left multiply by A inverse, I get H equals A inverse B, H prime. This is an element of H. So AB inverse, yeah, is because this is an H too, right?
Yeah, you could write multiply the H prime over and then you have it a little bit cleaner.
Oh, say that again.
Like if you write multiply by H prime inverse.
Yeah, I
then
like
you have
that.
By closure.
I think that's a cool, yep, yeah, I like, that's actually a much better plan. So this is equal to H prime inverse like that. And this sucker is definitely an H, yeah. So we believe all those things for the most part. Can somebody give me a nice proof of 6? Using things we've already proved. Or your own method.
Well,
How do we, yeah,
prove
go
on
ahead.
the 4 that AH equals BH
In certain circumstances, right?
if A is in BH.
Yeah, but here we don't necessarily have any of those hypotheses. Why would this be true in general? Could you help me construct an one-to-one and onto map between AH and BH? How would we do that? How would you build a bijection between AH and BH?
Is this implying that if AH equals BH, then their orders are equal?
It's saying that all cosets are the same size, even if they're not the same coset. So it's a little bit different than what you're saying. If they're equal, certainly they're the same size,
So
Sophie.
we're saying all cosets are the same size?
Yes. Yes. So how do I build a one-to-one and onto map between these two cosets? So I take something out of here, it looks like this. What do I do to it to get over here?
Multiply by,
Yeah, so phi of x does what?
left multiply by A inverse.
So A inverse undoes that,
Yeah.
yep, and then B
Yeah.
x.
Yeah.
So now look, this map here is going to turn AH into BH.
You have to prove that's not.
Gotta prove it's, yeah, you're right, yeah, I gotta prove, it won't be an isomorphism, but it will be a
Bijection.
bijection, yeah, cause these won't be groups, but
Yeah, that's right.
that's all good, yeah, it's great conversation. So, phi is 1-to-1, so I'm gonna assume that phi of x equals phi of y. Can you prove x equals y? And then I'll do the onto, phi is onto, let's take a z in BH, or I'll make it even easier. Take BH in BH. Show. Solve phi of x equals BH. What do you gotta put in there? do this like slowly and granularly, or you could use some bigger ideas to just, why do I know x equals y? What do I do? Well, how would you solve this equation in a group?
Multiply by B, A inverse.
Exactly. So these are both just elements of the group G, B and A. So their product, the inverse is in there, this is closed, so this is back in G. So just left multiply by, as Cormac said, BA inverse, which is AB inverse. And that would work too. And then that gets you x equals y. How do I spit out a BH? What does x have to be BH? And to solve this, I would just go to my definition. I know that phi, as I've defined it, is BA inverse x is BH. So this is BA inverse x equals BH. What does x need to be to solve that? AH. And that happens to be an element of what coset? A capital H, which is what we needed. We picked something from the domain, the range space, and we showed that the solution, the thing that hits it, is an element of the domain, AH. We've got a one-to-one and onto map. Those have the same cardinality, whether they're infinite or finite. That's how you show things have the same size. So, so AH and BH have the same cardinality. And we showed it. And yeah, time's starting to, luckily these last results kind of kick a little faster than these. We needed to understand how you work with these cosets, and that's why there was a little bit of slow going on the first one. But we can rock out Lagrange's theorem. And so before we get into it, I want to talk about what we do know. You're going to say, don't we already know Lagrange's theorem? And we do, but only in a special case. We only know a version of Lagrange's theorem in the case of cyclic groups. So all we know about so far, about order of the element divides the order of the group, that's all cyclic group stuff. Lagrange's theorem is for any group. So Lagrange's theorem, huge, and this is actually what you need to do one of your homework problems. The one where you've got like a subgroup that's like between size 420 and something else, I forget what it was. But Lagrange's theorem is how we can decide on what sizes are possible. And let's do it, let's prove it. The proof's gonna be one board because of all the work we've already got. So getting the hypotheses up here, G is a group. It is finite order. And H is a subgroup of G. And Lagrange's theorem says then the order of the subgroup divides the order of the group for any group, not just cyclics. So whenever you have a subgroup in a finite group, this is all about finite groups, the order of that subgroup divides the order of the group. So let's do a proof. Since H is a subgroup of G, I can form cosets. And I know that I can form a bunch of cosets from this, and they're either the same coset or they're different. So what you could do is you could take every single G and G and form this coset. You could literally run through. There's a finite number of things in G. Take everything in G, form the coset. So you've got G1, G2, G3, and suppose there's n different G's in there. So G is equal to G1 up through G sub n. So form all these guys. That they might all be different, but they're either different completely or they're the same. So some of these might be repeats of each other. So we know by property 4 that there's a finite list of these things. So we're gonna let G1H, G2H, up through G sub n, let's say G sub LH, be the distinct cosets of H and G. And there's a finite number of them because this is a finite group. I'm gonna run out of space at some point. So form all the different cosets you can get, put the ones together, and grab one that represents a group of them and write that list out. Yes, ma'am? Yeah.
So, so would this be like mods a little bit? So like, that's what we're pulling out is like,
Totally.
okay.
This is the generalized mod.
Okay.
Absolutely. Yeah, perfect. So, yeah, good insight, Penelope. So we've got these guys here. Now, what do I know about them? I know they're all the same size. LH. And in fact, they're exactly the same size as what? A coset is as big as
Any other coset?
and also as big as the subgroup itself. Right? Because you're just taking this guy and multiplying by everything, so it just gives you a whole new list of the same size. So these are all the same. So that means that I can write G as a union of these things. I also know they are disjoint. So also GKH intersect GMH is equal to the empty set if K and M are not equal. So any two of these, because I picked different representatives, these are completely disjoint. So look at what I've done. I've taken G and I've written it in a decomposition of cosets. So G1H, union G2H, union all the way up to G sub LH. And this is a disjoint union. So it's a partition of the group G. Let me stop.
Didn't we have some like examples where like K and M weren't equal, but they created like the same coset?
Yes, that's true, but what I'm saying here is these are, so what I've done, Christian, is
Yeah.
I've gone through and grabbed representatives of
Oh,
the different ones.
Okay, I see.
Does that make sense? Yeah. So that's this word here, distinct, is getting my ass out of trouble. It's all good, it was a good question. So look at what I've done. I've broken G, so I've got G, I've broken it into a bunch of pieces that are exactly the same size. And it doesn't look like it here because there's, but these are all the same size. So the size of each one of these added all up gives me the size of G. So because G is the decomposition of those things, the magnitude of G is the magnitude of G1H plus the magnitude of G2H. There's no intersections here, so these counts are true. And this is equal to L times the order of H, because each one of those is as big as H. And there's L of them, right? There's L of these guys right here. So the order of G is L times the order of the subgroup. That's a whole number. This is literally the definition of divides. So the order of H divides the order of G. And it's all just because of those coset properties. So that's a very profound result that we've knocked out easily because we paid a heavy price doing all that coset stuff at the beginning. Let me stop for a second and introduce one last bit of notation, this L here, the number of copies of H that give you G is called the index of H and G. So define the index of H in G to be the number of distinct cosets. Of H in G. And you write, use this bracket notation G colon H. This is the index of H and G. And it's literally equal to the order of H divided by, the order of G divided by the order of H. So let's just do a quick example here. Let's go to, say, D4. So dihedral group 4, it's the symmetries of a square. Let's take a look at one subgroup. H is equal to, let's do one of the flips. So identity, comma, some flip. I don't know which one, pick your favorite, doesn't matter. What's the size of this group? Do you remember how big the dihedrals are? 8? 8? Should be, yes, twice. It's twice. Because you've got the 4 rotations and the 4 flips. Does that make sense? So the order of D4 is 8. What's the order of H? 2. So the order of H. So how many cosets of H are in D? 4. So the index of H in D4 is 4. There's 4 of those, 4 distinct cosets. What about this? What if I took the rotation subgroup of D4? So let's look at identity, rotate 90, rotate 180, rotate 270, and call this my H. How many cosets of this guy are there in G? 2. Because it's got to make up the whole group, the cosets at the end. So this has order 4. So the index of this group in the subgroup in D4 is equal to 8 over 4, which is 2. 2 distinct cosets. And that's how you can know when you got all your cosets as well, right? You can be like, oh, there's only this many cosets possible. I'm good to go. This is how you do, so this and some reasoning and deduction will be how you do that one problem. All right. Any questions? Because I want to keep rolling. We got 10 minutes. Maybe come in with some, maybe we'll spend a little time on Wednesday working on those problems. Maybe I'll introduce like what's coming up, and then we can spend time working together. Does this sound okay? Yeah. All right. I got you. All right, so let's look at these corollaries on the back of that page. Bless you. And maybe you can kind of help prove these. So this first corollary is that if I have a finite group and I have an element in the group, then the order of that element divides the order of the group. Why? Using Lagrange's theorem. And hell, we might actually have to talk about Fermat's little theorem, I think, on Wednesday. I think it's gonna have to happen. I don't think it's happening today. of a subgroup can you form from a single element? Let me help. Cyclic subgroup. So I give you an A. So given this A, we can form the cyclic subgroup of A. And that's got the identity, A to the first, A squared, on up to A to the order of A minus 1. 1 less than the order. And then the full order would take me back to E again. So I've got this Z mod order of A minus 1 kind of thing going on here. So this is a subgroup. What do I know about the order of this subgroup?
The order of that.
It divides what?
Oh, it divides the order of G.
It divides the order of G by Lagrange. Right, so look how this worked. We took an element, we said, hey, form the cyclic subgroup generated by that element. That's a subgroup, so this is a subgroup of G. And its order must divide G, but its order is the order of A. The order of the cyclic subgroup is the order of A. So this is, by nature, the order of A, and it divides G, so we knock it out. I'll bring in some other examples of some things that'll help on your homework too on Wednesday. I kind of got a feeling it's going to be work day with some talking about this stuff. Let's check out that next corollary. If the order of G is a prime, P, then G is cyclic. Now, first off, this is crazy because one of the big problems in group theory is, can we classify every group of every order? And what this is saying is that if a group has prime order, it's automatically cyclic, and we know that. And we understand that because that's literally the first half of the class. So let's take a look at this thing here. If G is equal to a prime order, then G is cyclic. So let's take an A in G. And I'm going to form the cyclic subgroup again. So it's again building that thing up. So then A is the cyclic subgroup generated by A. And we don't quite know what the order is, but we do know that the order of this, so let's put A to the order of A minus 1. I do know that the order of that A has to divide the order of the group. Right? So the order of this A must divide the order of the group. But that order of that group is P, which is prime. What are the possible orders of A? Or P. So there's only 2 possible orders of any particular element. So the order A is equal to 1, or the order of A equals P. If the order of A equals 1, what's A? That's just the identity. Yeah, that's your identity element. So this implies A equals E. But if the order of A is P, then the order of the it's everything. Yeah, it's everything. So if the order of A is P, and you take the cyclic subgroup has order prime P, and that's the order of G. So G must be the whole dang cyclic subgroup. They have the same, you've used up everything in G with the powers of A. So really cool, really powerful things. Hey, can you do, we've got a few minutes. We can maybe start the Fermat's thing. We could also hold off on it. Could you actually do that final corollary? Using results you already have. So that final corollary, you have a finite group, you have an element of the group, A to the order of G is E for any element A. Why is that? Okay. Do not look at this. Do not look.
No.
Yeah. Yeah, good. Think you got something? Yeah, what you think? Yeah, that's it. Yeah, that's it. Christian, can you walk me through this, and then we can leave? You know, everybody will be happy and you'll be a hero.
So, you could get the, cyclic subgroup generated by A.
Okay.
Which is the subgroup G. You know that, like the order of A divides the order of G.
And we can just go straight to this, I think. Probably, yeah. Yeah.
You can rewrite that as G, the order of G is equal to, the order of A times N for some integer. N, which means that you can then rewrite A to the order of G as A to the order of A times N. You know that A to the order of A is just E.
Yes.
And then E to the N is E.
Lovely. Yeah, beautiful. So that Fermat's little theorem, I always spend most of my weekends preparing for y'all. Calc is just like, what are we doing for the next month? I've got that covered. But this class is always like, what are we doing? Shit, I better bust my ass this weekend. So I busted my ass, and I have two proofs of Fermat's little theorem that I want to show you. One actually uses all the heavy machinery we've got. It upsets me. So I was like, I want a different proof to feel like I understand this, so I learned a different proof, and we'll talk about those on Wednesday. And then I'll bring in some examples to kind of help on some of the other homework. Does this sound okay? Yeah. Another chill day in algebra. I'd rather have us understand shit than just plow through it, so. Oh good, that's recorded. Great.